Hey kiddos, welcome back. Today we're going to start talking about the mole concept in chemistry. It is not the brown furry creature that they talk about in biology that burrows underground. The mole concept is different in chemistry. Let me introduce it by talking about different ways I could count things. Pretend I had a large stack of paper, and let's say the stack of paper was this tall compared to the Empire State Building. Suggest a way to count that paper other than counting it one sheet at a time. By the way, can you imagine a stack of paper that tall? It would take forever to count it one sheet at a time. However, what if I knew the mass of that stack of paper? What if I were able to determine how much that stack of paper weighed, and I were able to find the mass of, 1,000 sheets of paper? If I knew the mass of 1,000 sheets, couldn't I then calculate the number of sheets of paper in a stack that was as tall, or many times taller, than the Empire State Building if I knew the mass of that paper? I could count the paper by weighing it, couldn't I? Yeah. What if I had a 50-gallon barrel of pennies? How would I count those pennies if I didn't have to count those pennies one at a time? Well, what if I knew the weight or the mass of the barrel full of pennies, and I knew the weight of just 100 pennies? Couldn't I calculate the number of pennies in this 50-gallon barrel by knowing the weight of just 100 of them, and dividing the total mass by the mass of my 100 pennies and getting the number of pennies in the barrel? Once again, I could count pennies by weighing them. Now, we do the same thing in chemistry. Atoms are so small that an ordinary sized sample of a substance contains so many of them, it becomes impossible to count them. The particles are submicroscopic. So, think about this. How do you think we count atoms? Yeah, we don't count them individually. It's impossible to do that. So we count them by weighing them or finding their mass. It turns out that 197.0 grams of gold has this many atoms in it. 6.02 times 10 to the 23rd atoms of gold. If I were to write that number out, it would be 602 with 21 more zeros after that 2. Sometimes I lose count. Let's see if I can do it. 3, 6, 9, 12, 15, 18, 21. Turns out that 197.0 grams of gold has that many gold atoms in it. So, if I weighed out 197 grams of gold, I would know it had 6.02 times 10 to the 23rd atoms of gold. Turns out that 107.9 grams of silver has that same number of atoms of silver. So I could count silver atoms by weighing them. If I wanted half this number, I would get half that mass of silver. It turns out that 12 grams of carbon has 6.02 times 10 to the 23rd atoms of carbon in it. Now, 12 grams is less than 1/3 of an ounce, yet it has this many carbon atoms in it. If I wanted to get 6.02 times 10 to the 23rd atoms of nickel, I would need about 58.7 grams of nickel. Now, where do you think I'm finding these numbers from? And don't you think this number over here, 6.02 times 10 to the 23rd, is sort of kind of important? Well, let me show you. Let's take a look at the periodic table. Let's find gold. So let's make this a bit bigger so we can circle it for you. Here is gold. And remember, we talked about silver, and we talked about carbon, and we talked about nickel. Now, there's something called atomic mass. Let's look at the atomic mass of these elements. For gold, it's 196.97. Well, we can say 197.0. For silver, it's 107.87, 107.9. For carbon, 12.01, and for nickel, 58.693, but we can say 58.7. These numbers here are called the atomic mass. It turns out that the atomic mass in grams has, you ready for it? 6.02 times 10 to the 23rd atoms of that element. This number, 6.02 times 10 to the 23rd, is called Avogadro's number, after the individual who calculated it. It can be written as, and we're going to write that down again, this time you try it with me, 602 with 21 zeros after it. I think I counted properly. It's often called the mole, M-O-L-E, and it's abbreviated with the letters M-O-L. So it turns out if I had 1 mole of any atom, I would have 6.02 times 10 to the 23rd atoms of that element. If I had 2 moles of any atom, I'd have 12.04 times 10 to the 23rd of that element's atoms. A mole is a very, very big number. We use it because atoms are very, very small. So, for instance, if I had 1 mole of carbon, we said that was 12.01 grams, and that is less than 1/3 of an ounce. And it would have this many carbon atoms in it. Let me give you just a couple of examples of how large that number of carbon atoms is. If I had 1 mole of marbles, just standard size marbles, they would actually cover the United States, the entire geographic United States, and that pile of marbles would be about 116 times taller than Mount Everest. Can you imagine that many marbles? If I had 1 mole of marshmallows, it would cover the United States, we'll use the U.S. again, about 6,500 miles deep. Once again, it is a huge number. If I had 1 mole of water molecules, it would be a little bit more than 1/2 of an ounce. So I'm going to say about 1/2 of an ounce. The number of molecules would be more than all the grains of sand on all the beaches in the world. This number, Avogadro's number, is that big. What does that tell you about the size of carbon atoms or the size of water molecules? That's right. They're very, very small. So we use the mole as a counting unit, and we count atoms and molecules by weighing them. So remember when we said if I wanted to have 1 mole of carbon atoms, it would weigh 12.01 grams? What if I had 6 grams of carbon? That's right, it's about half of 12. Wouldn't I have half of Avogadro's number? 3.01 times 10 to the 23rd carbon atoms. You see, if we can weigh out carbon, we can determine how many carbon atoms are in that sample. And it turns out we can do that not just for carbon and not just for water, we can do it for any atom or molecule. And that's what we're going to be practicing in the next video. All right. See you soon. Bye-bye.